Welcome to the STEM Pathways with Rohan Sharma podcast, where we dive into the exciting world of science, technology, engineering, and math. In each episode, we share exciting stories, groundbreaking research, and inspiring interviews with experts and enthusiasts who are pushing the boundaries of innovation. Whether you're a student or professional, or just curious about how the world works, join us as we explore the endless possibilities of STEM. Let's get started. Today, I'll be interviewing Sara Campbell, who holds a bachelor's in physics from MIT and a PhD in physics from the University of Colorado Boulder. How are you doing today?
Hey, how's it going?
So to get started, I wanted to ask what made you choose your major of physics for MIT, and what was your experience like at Phillips Exeter for high school?
Yeah, let's see. I think I was a little bit torn between math and physics at the time. So I think originally I was gonna like double major in both. And then yeah, I think I was just always interested in like in the world and how, like math is sort of like the language in which the universe seems to express itself, and that's like kind of magical. And I was always interested in that. I always definitely liked math. I think yeah, at MIT I got more involved in like sort of like more hands-on work, and I think I really enjoyed actually like using the machine shop and like building stuff with my hands and like building my own physics experiment or whatever, building lasers. And so eventually I decided, oh, I want to do actually like experimental physics because that's more hands-on. And yeah, I eventually chose that path. Um, but yeah, back at Exeter, yeah, it was just like random. Like my parent, like I'm from New Hampshire. I'm like from that town. So yeah, as I was thinking about where to go for high school, we did happen to live next to some private school. I didn't really like know anything about it beforehand, but like definitely my parents encouraged me to at least apply and like look at it, like consider it. Initially I was like pretty set on not going because all my friends were going to the public school and I wanted to stay with my friends. But yeah, I think when I visited the school, um, after I got in, there was like, yeah, this one math teacher who like wrote the whole math curriculum, and you kind of like there, I think you sort of like almost like teach yourself math by like working through a bunch of problems that like guide you through sort of new concepts in a really like brilliant way. He was super awesome. And yeah, I think just visiting the math classes there like really encouraged me to attend, and I'm glad I did. And yeah, I think especially like the math education there was really good. I was certainly very lucky that I had that opportunity early on.
So what was your experience like at MIT?
Yeah, MIT was super fun. I feel like there was like lots of like sort of crazy people from all over coming there. People would be doing like strange things at all hours of the night. Like if you walk through the hallways there or whatever, somebody might be like, juggling in the middle of the hallway at like 2 in the morning. And yeah, I always thought it was just like seemed like a really fun, sort of like creative place. I think it certainly had like the nerds of the nerds and like, I think people really came out of their shells there a lot. People were like not maybe quite as self-conscious as we were in high school or whatever. And I think it gave us a lot of freedom to sort of like, yeah, be ourselves, do strange things. Um, and definitely like, learned a lot. I didn't like always go to class because I was kind of lazy, but like, these big lectures, I think you can kind of sometimes get lost, or if you want to sleep in, like nobody cares if you show up or not. But so like, yeah, I think for some people, like a smaller liberal arts college might be better in that regard. Like, the professors, they're great, but like, yeah, some of the class sizes are definitely huge. But I think like, yeah, what I really liked about MIT was all the opportunities to get involved with research as an undergraduate. So like if I recall, there's like, I don't know, like 4,000 undergrads, but there's like more grad students than undergrads for sure. And so there's like so many labs doing like, world-class research. And it seemed like basically every undergrad who wanted to was working in a lab. And I think like working side by side with um, more senior scientists was super helpful and like super helpful for yeah, me like figuring out what I wanted to do in the future. So, I think every university you can always do something like that, or if you go to a smaller school with like less of a research program, you can always apply to like REUs, like research experience for undergraduates, um, and like, do research somewhere else for the summer and stuff like that. I do think at MIT it was like super easy to just, cold email a few professors and just get in with some random lab like to get started. So that was really nice.
So, why'd you decide that you wanted to keep going in your education and get a PhD?
Oh, why did I decide? Was the question?
Yeah.
Yeah, let's see. I guess just because I was working in the lab. So yeah, I was having a lot of fun with what I was doing then. And like I think when you get the PhD, most of what you do is you just like show up and work in the lab. Like, there's like 2 years, your first 2 years are classes, but like the vast majority of the PhD is like, you're not really like you're in school, but like um you're mostly just doing like research or whatever. Um, so yeah, I saw the grad students who I worked with. Of course they, worked very hard and sometimes didn't sleep enough, but like other than that, like it seemed like they were you know, enjoying life. They were kind of doing what I wanted to do. So I decided yeah, that's what I would do next.
So, what made you go with the University of Colorado Boulder?
Yeah, it's like kind of a random place. It's like in the middle of the country, and it was I think like back in like I'm probably gonna get this wrong, but like the 50s or the 60s or something. Like the U.S. government decided they wanted to make like a NIST, like National Institute of Standards and Technology, like campus also in the middle of the country. Um so yeah, I think that it has just like a really good legacy in my field in particular, which is like sort of like atomic physics or atomic and optical physics because it has really close ties with yeah, like NIST, like the national lab that's right nearby. And so yeah, it's been really historically like pretty strong and the kind of stuff that I like to do, which is like play with lasers and atoms and, do sort of tabletop experiments where I'm turning lasers on and off and, changing the little states of, well, now qubits, but at the time I was making like an atomic clock out of quantum matter or whatever. And so, yeah, it seemed like a good place, really good place for that. Usually when you choose like where to go for your PhD, you don't always have to, but it's usually like pretty common to also choose your PhD advisor, sort of when you're looking around at different schools. So there's like one lab in particular that I was pretty interested in. Like I was always sort of interested in like the fundamentals of the universe or whatever, and like I did work in like particle physics for a while as an undergrad because I was curious, um, about like sort of maybe more like reductionist perspective on the universe and like all these like subatomic particles and like stuff beyond the standard model of particle physics, like just the remaining stuff we can't really explain. And I was like sort of interested. So you could tackle that in like big particle accelerators where you're smashing stuff together and kind of seeing what comes out. You can also look at this stuff sort of on a tabletop with like atoms and lasers and stuff like that, where you're looking at these fundamental particles of the universe maybe just causing a very small perturbation on something that you're measuring like very precisely. So that's kind of like this whole field of precision measurement, and where when people do like precision tests of beyond standard model physics, um, it's sort of like we're looking for anything else in the universe that we haven't fully explained, sort of causing a really, really tiny like perturbation on, say, like the resonant frequency in an atom or something. And that was actually how they like one of the first signs back in the day that they were gonna eventually come up with like quantum electrodynamics where they realize, oh, actually like instead of the electron just going from here to here in some straightforward way, it actually like, virtually it's doing all these other sort of things as well. And you have to also correct for these. Like I think it was sort of like a precision measurement experiment where you're very precisely measuring a particular frequency that sort of first uncovered that. And so, yeah, there's a lab at the University of Colorado that was working on that. Like June Yee's lab, he was my PhD advisor, and yeah, I thought that was like really cool. It was like both, like hands-on work that I really enjoy. Lasers are fun. Using a wrench is fun. I don't know. And it was also sort of like uncovering sort of like, yeah, the underpinnings of like very fundamental science. So that was probably my ultimate um decision was like, yeah, sort of because I wanted to work with that advisor at that lab.
Yeah. So I saw you did a postdoc at Berkeley and then you started working. What was your first job?
Yeah, my first job, I guess I was like 30 or something, was actually the job I still have now. So originally we were part of like Honeywell, like that you might know from like making thermostats or whatever. And so yeah, Honeywell for whatever reason, which was awesome, decided to make yeah, sort of like a quantum computing division. And a lot of my friends from grad school had actually moved back to the sort of like Denver area, and they were all working at this company. They were all super happy. And yeah, I thought I might give that a try. I mean, to be fair, like to tell people, if people are in high school or college listening to this in terms of like things that pay you money, like when I was working in a lab as an undergrad, it wasn't like I was rolling in cash, but like, they do pay you to do the, to do the lab research. And if you can always do summer internships. I think now those are more common in the field of like quantum computing or whatever. They probably do pay a little more than the university would, but yeah, I always got paid for doing my work at least. And uh, yeah, if you go, I think some master's programs like require you to pay tuition, but like PhD programs, you always get like a stipend. Not like not enough to be like really living large or whatever. Like my software engineer friends always like, seem to be like living the life or whatever. But it was enough as like just like a normal single, don't need fancy things kind of person to like pay rent and buy food and stuff like that. And your tuition's covered as well. So I think that's something like not talking to people, if people like go to a smaller college or something, that's something they don't always know is like usually a STEM PhD, it's like tuition's fully covered and they pay you money. Yeah.
So what do you do in your job right now?
Yeah, so I'm in charge of an experiment or actually two experiments now to start looking at using photonic integrated circuits with trapped ions. And so yeah, our company's making trapped ion based quantum computers. So we have these little like chips and little like single atoms are floating above these chips with electrodes on them, and we're like sort of suspending them in air. Well, not in air, in ultra high vacuum, I guess. And we're like shooting them with lasers to manipulate their atomic states. Like sometimes we bring the two ions together, they interact with each other and with the lasers to cause like the bits in the quantum computer to flip and stuff like that. And so we use lasers all the time to like control the ions, do our gates, do our logic gates, and then we also use lasers to like after we do a computation to read out what the answer is at the end. And so that's all like fine and good. But to really make a useful quantum computer that can like tackle problems that are relevant and interesting for industry, I think we need like more like 1,000 qubits or more. Right now, our machines are, I think the latest one we released has like 56 qubits, and we're going to continue to scale up from there. But yeah, I think it's going to be a big challenge to scale up um, the qubit count without um, finding some way to deliver the lasers to the ions in a more like scalable manner. So yeah, the work I'm working on is like trying to put all these lasers that we're currently like shooting at them from like outside this big vacuum chamber, and we're like literally using like mirrors and lenses that are like this big and stuff. We're looking to scale all this down and like integrate it in the chip with the ion, so that instead of having to like shoot a laser beam precisely um, at some ions to do a good gate, the laser light will actually just like come right out of the chip, and we don't have to like actively align it or anything, which is great. Um, but there's just like a few remaining challenges, I think, with like having the light um inside the chip so close to our qubits. That like yeah, it can cause a few things that sort of like, perturb the state of the ion. And so the research I'm working on is like sort of like the surface science involved with that, like there's little effects, like if you have like actual light coming out of a surface, um, what's that going to do with like the surface contamination or whatever? If there's a little layer of something, how does that interact with the light, and how does that like jiggle the ion around in a bad way or whatever? And like I'm just trying to like sort of prototype and like prove out yeah, future technologies in the system that we have not. It's like more of an R&D project, and like we'll eventually figure out how to like integrate these things into a real commercial quantum computer.
Yeah. So for my last question, I wanted to ask if you have one piece of advice for someone who's still in high school or early in college wanting to follow a similar career path as you.
Yeah, I mean, I would say like if you want to do experimental physics, which is like sort of what I ended up doing, sort of no matter what field you're working in, I think getting some hands-on experience in the lab would be really great. And I would just like be persistent, apply to just keep like cold emailing professors. They don't even need to be at your university. You can apply to like a number of summer programs, so REUs, or I actually did a internship as well, like through the SULI program, like SULI puts undergraduates at like I think Department of Energy labs or something like that. So there's lots of undergraduate research opportunities, and like, I think a lot of in life in general, I think a lot of these like application processes and stuff are like completely random. So I think just send out a lot of applications, and you'll get something. And I think yeah, getting in somewhere there, like that's really where you'll find your mentors. That's where you'll get like good experience. That's sort of where you'll get sort of like letters of recommendation for grad school or whatever. Um, and yeah, I would just like hop around and like, maybe I thought I was going to do particle physics initially, and I ended up doing like experimental atomic physics or whatever. Like, just hop around and don't worry too much. Like, just if you're not enjoying what you're doing, just try something else, and I think something will eventually stick. Yeah.
All right then. Thank you for joining me on the podcast today.
Thanks.